12.1. Did I start that? I did start. Tangents. All right. Anybody know what we mean when we say a line or a segment is tangent to a circle? It's sort of related to SOHCAHTOA, but we're talking about tangents, different kind of tangent. Any ideas? No? A tangent to a circle is a line or a segment that intersects a circle in exactly one point. So our picture, if we draw a picture of a tangent, what we're looking at here is something like this, and it touches the circle in just one point. And we call that point the point of tangency. Or the tangent point. And we call this line, or the segment would be the tangent line or the tangent segment. And so nice things happen when we have tangents to circles. Point is it touches the circle in one point. Tangents to other graphs, tangents to graphs in general. Important idea in math. You'll talk about tangents a lot, tangent lines, as you go forward. It's an important idea in math. Tangent comes from the Latin. It means to touch. So tangent just means we're touching the circle in one point. All right. So, are we good with what we mean by a tangent? Tangent line, tangent segment. So our big theorem today is the tangent theorem. Tangent theorem tells us if a line is tangent to a circle, then it is perpendicular to the radius at the tangent point. So that's one special thing that happens with tangent lines. So let's draw, so the picture we're talking about here, there's our circle, there's our tangent line. If we were to draw a radius to the tangent point, let me undo that, I want just a segment, there we go. That would be a 90-degree angle. And if we were to write this out with symbols, we would say that line AB is tangent to circle O at P. So OP is perpendicular to line AB. So that's one of our special things that happens with tangent segments to circles, tangent lines, tangent segments, perpendicular to a radius. Couple of important things in chapter 12. So often when we're solving problems in chapter 12 when they have to do with circles, we need to remember two things. All radii are equal. So it doesn't matter where in the circle we draw the radius, they're all the same length. And when we have problems that have to do with circles, I'm going to say when in doubt, draw a radius. And we want to draw it in a helpful place, but if we draw a radius, we can take advantage of the fact that all of them are equal, all of them are the same length. So often in chapter 12, we have to draw additional radii to help us solve problems. All right, so let's look at a couple of examples that have to do with this idea of tangents and perpendiculars to radii and that kind of thing. Are we good so far? Okay. Here's our problem. There's a circle. And I'm going to do this. AB and AC are tangents to the circle. Find X. So what are we going to do? Well, they're tangents to the circle. These are radii. What are these angles? This angle and this angle. Tangents intersect the radius at 90. So that's 90. That's 90. What kind of shape is this? How many sides does it have? It's the kite? Quadrilateral? What do all the angles inside a quadrilateral add up to? 360. I know 3 of them. Can't I figure out the 4th? Yep. So I can say 90 plus 90 plus 152 plus x has to equal 360. So 90 and 90 and 152 is 332. Subtract 332, and I get x equals 28 degrees. So we took advantage of the fact that the tangent and the radius make a 90-degree angle. All right, questions there? All right, let's look at another one. For this one, we have an airplane. Is 6.5 miles above the Earth. The radius of the Earth is 4,000 miles. How far can the plane see on the surface? So let's draw a picture to help us out. Here is my Earth, looking at the Earth from the side. Here is the airplane, and this distance here is 6.5 miles. We're going straight up 6.5 miles. That's how far above the surface of the Earth it is. And it wants to know how far can the plane see on the surface of the Earth. So we're looking out here, and the furthest that we're going to be able to see is when our line of sight is tangent to the Earth. So we can see to the tangent point. So there's my tangent point. And that's what we want to try to find. We want to find that length. What are we going to do here? It's going to have something to do with a triangle. It says the radius of the Earth is 4,000 miles. There's the center. Let's draw in a radius. Here's a convenient place to draw a radius. Because what does that make this angle? 90 degrees. Where would be another convenient place to draw a radius? To the points where we measure directly overhead. There we go. This is 4,000 miles. This is 4,000 miles. All radii are the same. Well, what kind of triangle do we have there? We have a right triangle. How long is this side? 4,006.5 miles. This side is 4,000 miles, and we want this side. We can use the Pythagorean theorem. We have a right triangle. Which side is the hypotenuse? The 4,006.5, that's the hypotenuse. It's across from the 90-degree angle. So we can say x squared plus 4,000 squared equals 4,006.5 squared. So we got some big numbers here. X squared plus, this is 16 million. Equals, and this is 16052, 042, 0.25. Subtract 16 million from both sides. I get x squared equals 52042.25. So to get x, what do? Square root both sides. Undo that square. And I get x equals 228.1 miles. So we can see 228 miles along the surface of the Earth. All right, questions there? Okay. The converse of the tangent theorem. The tangent theorem says that if a point is tangent to a circle, then it is perpendicular to the radius. The converse, we just turn it around. Converse says if a line is tangent, or if a line is perpendicular to a radius, then it is tangent to the circle. So if it's perpendicular to a radius on the circle, then it is tangent to the circle. And our picture looks exactly the same. We're just using it. We're just using this in reverse. Oops. So we're saying that we know that this line is perpendicular to the radius. That guarantees us that it is tangent to the circle. Our drawing looks exactly the same. So we're going to say if line AB is perpendicular to OP, segment OP, then line AB is tangent to the circle. At point P. So we can use this idea. We can use tangents to decide if we to decide that we have a perpendicular segment to a radius, and we can decide if we have a perpendicular segment to a radius. That guarantees us we have a tangent. All right, we good there? So let's look at a couple more examples. There's my circle. All right. That's X. This is a 90-degree angle. This is 24, and this is 18. And we want to find X. Well, what are we going to do here? Well, Pythagorean theorem, that's a pretty good idea because we have a right triangle there. But we only know this length. Well, how long is this piece? X. It's also a radius. Well, if that's X, how long is that whole side? 18 plus X. You have to add them together. Now we can use the Pythagorean theorem. Which side is the hypotenuse here? 18 plus X. So I'm going to say that X squared plus 24 squared equals 18 plus X squared. All right, what do I do with this? What do I have to do with this 18 plus X squared? $18 plus X squared is the same as 18 plus X. times 18 plus x. I'm multiplying it by itself. What do I have to do to this? FOIL. I have to FOIL this. It helps you out. Write out your initials here. FOIL. FOIL tells me first 18 times 18 is 324. Outside, O is outside. 18 times x. Inside, I is inside. 18 times x. Last, x times x squared. I'm adding those together. So I get x squared plus 24 squared is 576. Equals, we're going to add all these together, 324. 18x plus 18x is 36x plus x squared. It looks kind of intimidating, but it's not too bad because I have an x squared on both sides. So what happens when I subtract that x squared? They cancel, they go away. So I get 576 equals 324 plus 36x. Now we're home free, this is easy. Subtract 324. I get 252 equals 36x. Divide by 36, and x equals 7. All right, questions there? Okay, let's look at another one. Here's our circle. And if you notice, a lot of these problems that have to do with circles turn into problems about triangles. That's often what we do in math, is we turn problems that we don't know how to work with into problems about circles. And then we turn problems that have to do with circles into problems with triangles, because Pythagorean theorem works for one. And we can also use SOHCAHTOA other times. So a lot of times we turn problems into circle problems and turn circle problems into triangle problems. All right. And I'm going to call this point A and this point B. And this says, is segment AB tangent to the circle? That's my question. Well, if it is tangent to the circle, what would that make this angle? 90 degrees. If it's tangent to the circle and that's 90 degrees, what kind of triangle is this? Right triangle. So how can we tell if that's a right triangle? That's what the question is really asking us. Is it a right triangle? Does that look like a familiar question? It's just like the opener. Is this a right triangle? Well, I know this side's 12, this side's 5. How long is this side? 9 plus, what is this? 5. That's a radius, right? All radii are the same. So that's 5. So that whole side is 14. So we're saying, is 5 squared plus 12 squared, does that equal 14 squared? 25 plus 144, does that equal 14 squared is 196? No, what is this? 169 does not equal 196. So, not right triangle. So it's not tangent. Because if it were tangent, that would have to be a 90-degree angle, and that would be a right triangle. So the Pythagorean theorem should work if that were a right triangle, if that were a tangent one. All right, questions there? All right, we have one last theorem. This one doesn't have a special name. Two segments that are tangent to a circle and have common endpoints outside the circle, or have a common endpoint. Are congruent. So what we're saying here, there's our circle. Here are our two tangents, two segments. Here are our two tangent segments. This looks like the picture we drew earlier when we were working on a different problem. Let me draw a better tangent segment. There's one. And there's one. We're going to call that A, B, and C. AB and BC are tangent to the circle. Segment AB is congruent to segment BC. Those two segments are the same way. And if we wanted to show why this is true, we would draw in two radii. The radii are congruent, so those segments are congruent because they're both radii. Those are 90-degree angles because they're tangent. And then I can draw in this segment in the middle, which is congruent to itself. So these two triangles are congruent by hypotenuse length, and corresponding parts of congruent triangles are congruent. So that's why that works out. So if we have two tangents that intersect outside the circle, we know the lengths of the two tangents are the same. All right, let's look at one last example. We have a circle, and I'm going to draw a nice triangle. There we go. And I need to connect this, this. And we know this is 14, this is 8, and this piece is 5. And we know that the circle is inscribed in the triangle. And the problem is find the perimeter of the triangle. Well, because a circle is inscribed here, that means it's tangent at each of the points. It just touches one side of the triangle, touches the circle in just one point on each of those places. So each of these segments is a tangent segment. That's what an inscribed circle means. So if these are all tangent segments, how long is this piece? 14. Those have to be the same. How long is this piece? 5. This piece? 8. So the perimeter is 8 plus 8 plus 14 plus 14 plus 5 plus 5. Adding all those together, and I get that it is, when I add those together, 54 units. And we were able to figure that out because all of those segments are tangent segments. All right, questions there? Okay.